So although tellurium and oxygen have the same number of valence electrons, 6, and so they both want two electrons, they could potentially lose 6 up to 6. They don't have to lose all 6. There's a difference in reactivity, and that difference in reactivity has to do with the size. Both of these are considered oxidizers because they want electrons. It's more difficult for them to lose electrons than to gain them. But which one do you think would be a more powerful oxidizer, tellurium or oxygen? That is the bigger one or the smaller one? Which one do you think? The smaller one. It's the case, the smaller one is more powerful. And in fact, oxygen is much more powerful oxidizer than tellurium. And so size is going to have an impact on chemical reactivity. How does it have an impact? Well, it has to do with electrical interactions. And so if we're looking at an oxidizer wants electrons because of the positive charge. And so the more concentrated that is, the smaller the size.
So just because it's like closer to the nucleus.
Closer to the nucleus. Although the nucleus charge is quite a bit different. If you look at tellurium has many, many more protons. Tellurium has 52 protons in the nucleus, whereas oxygen only has 8 protons. So a huge difference in the number of protons. But it's a little bit more tricky than just looking at the number of protons. It has to do with the size. The size is an indication of how the electron cloud is being pulled in by the nucleus. The more strongly it is, the smaller the size. So let's look at size now, trends in atomic size. Basically, the smallest atoms are where in the periodic table? We could summarize this slide in this way. The smallest atom is hydrogen or helium. I asked you this a long time ago. Helium. So the smallest atom is helium, top right. The biggest atom is francium, bottom left. So the size increases going left to right. Or not increases, decreases. Size decreases going left to right. Size increases going from the top to the bottom. So why does the size shrink down? I talked about hydrogen and helium. It's because the more protons you have in the nucleus, the stronger the pull on the electrons. So helium has more protons than hydrogen. But why does the size increase as we go down? Because as we go down, the number of protons increases dramatically in the periodic table. Let's take a look at the periodic table here. So hydrogen, 1 proton, helium, smaller. But then lithium has 3 protons, so lithium should be smaller still, but it's bigger. Why is lithium bigger? Yeah, because we have another shell of electrons. And so each time we're going down the periodic table, we're adding another shell of electrons, which causes the atom to become bigger. And so that's what we have here. This slide. The same thing. What they're saying is this is going down. Highest occupied principal energy level is valence shell. And so all they're saying is that n equals 2 is like this, n equals 3, n equals 4. So as you get to higher energy levels, the orbitals would get much bigger. And then this is the tracker effect, the more protons. And so the smallest atom on this is helium. The biggest atom here is cesium. Francium's radioactive. They only went to this row here. And you can see, as we go left to right, what happens? It gets smaller because more protons, stronger pull on the electrons now. And then the size increases as we drop down because we're getting to higher and higher energy shells. More shells. Size is going to have an impact on reactivity. And so which one do you think is going to be a more powerful oxidizer? Fluorine or chlorine? Fluorine. Fluorine's more powerful. In fact, that's what we see. When we look at the redox chart, it goes fluorine, chlorine, bromine, and iodine. Iodine's way down there. Fluorine's at the top. That makes sense. The same thing should hold over here. The biggest atoms are the easiest to steal an electron from. And so we would expect the most powerful reducing agent here on this chart to be lithium is the one you memorize. We expect francium to be the most powerful. Francium is very dangerous. Cesium is much more dangerous than lithium. Cesium can catch on fire when exposed to air. And so you can't expose cesium to air. It's that dangerous. But our chart doesn't quite make sense because the bigger it is, the easier it is to strip an electron off of. So cesium should be the easiest, followed by rubidium, followed by potassium, sodium, and lithium. But when we look at the redox chart, what's at the top of the reducers? That is the bottom of the chart. Let's take a look at the redox chart here. We see the most powerful reducer is lithium. In fact, as far as this order goes, I would have expected potassium to be a much better reducer than lithium. In fact, it is. Lithium reacts slowly with water. Potassium reacts explosively with water. Potassium is much more violent in reaction with water. You can see this. Let's take a quick look. We look at lithium and water, the reaction. Hopefully this is a decent video. I didn't have a chance to see it first. Well, this is sodium and water. This is
mineral oil minimizes reaction to the oxygen in the air. If we remove a piece of potassium metal, we can see that potassium is coated over with a gray coated.
Oops, sorry. I thought I was going to close this bar, but I guess I didn't want to close that bar.
Down the column of potassium, we see that the potassium metal is also stored under mineral oil to minimize its reaction with the oxygen in the air. If we remove a piece of potassium metal, we can see that the potassium is coated over with a gray coating of the oxide. As we continue down the column, group 1 metals get softer and softer. The potassium cuts very easily. As we cut through the metal, we expose the shiny metal surface underneath. The potassium is extremely soft. We can easily flatten out the potassium metal has the consistency of cream cheese. The potassium is a metal and is an excellent conductor of electricity. We add a piece of potassium metal to water, we see that it reacts much more rapidly with the water than the sodium. As you go down the column, the ionization energy decreases and the metal reactivity increases. The reaction is very exothermic, and the hydrogen that's produced ignites. We can test for the formation of potassium hydroxide by adding phenolphthalein. The solution turns red-purple due to the formation of potassium hydroxide.
Okay, that was potassium. Take a look at sodium. Sodium is bigger or smaller? Smaller. Sodium is smaller, so do you expect it to be... now this is very tricky because I just asked you about fluorine and chlorine. So fluorine was smaller, right, than chlorine? Which one's more reactive? Fluorine's more reactive. Sodium is smaller than potassium. Which one's more reactive? Potassium. Why? Why did I just flip-flop? The reason I flip-flopped is because they're doing different things. Fluorine and chlorine are oxidizers. They're taking electrons. So if fluorine's smaller, it's going to be more powerful of an oxidizer. However, potassium and sodium are reducers. They're losing electrons. So which one's easier to steal an electron off? A big atom or a small atom?
Big atom.
So it's not flip-flopping. It's totally consistent. Sodium is going to be holding on to the electrons more tightly because it's smaller. Fluorine holds on to its electrons extremely tightly. And so sodium is going to be less reactive. So let's see if it's less reactive here.
We'll go down to the column on the periodic table in group 1 and look at sodium. Like the lithium, the sodium is stored in the mineral oil to minimize reaction with the oxygen in the air. If we remove a piece of sodium metal, we notice that it's also coated over with an oxide coating. Group 1 metals become softer as you go down the column. The sodium is much easier to cut than the lithium. As we cut off the oxide layer, we can see the shiny metal underneath. It coats over very rapidly with a layer of oxide. The sodium is a metal and is an excellent conductor of electricity. If we take a piece of the sodium metal and add it to water, we notice a much more rapid reaction with the water. Like lithium, the sodium is less dense than water and floats. The metal moves across the surface, being pushed by the hydrogen gas that is produced. As you go down the column with group 1 metals, the melting point of the metal decreases. The reaction is very exothermic, which causes the sodium metals to melt.
It should
The
ignite
metal
too.
contracts into a very compact spherical form. We can again test that hydrogen gas is being produced by this single displacement reaction by trapping the gas and testing its flammability.
If you get enough sodium, it'll ignite without having to do this.
We can test for the fact that we produce sodium hydroxide by adding phenolphthalein. Phenolphthalein turns a purple-red color due to the presence of the hydroxide.
All right, so sodium, did you see it's a less violent reaction? Still pretty violent when you look at the disposal. It can be very explosive, so you gotta watch out. Depends on how much you have. If you put a little larger piece, it would have ignited. Let's take a look at lithium.
Group 1 metals are very reactive because they have low ionization energy. One of the ways that indicates its high reactivity is the way that we store the metals. Group 1 metals are typically stored under kerosene or mineral oil to prevent or limit the reaction with the oxygen in the air. Let's look at some of the physical properties for Group 1 metals. We'll start out with lithium. The lithium is coated at this point in time with a layer of both the oxide and the nitride. And we end up with a fairly dull gray appearance. Group 1 metals tend to be relatively soft, and we can easily cut the metal with a knife. What we can do is we can see the shiny metallic surface underneath. If we bring in a conductivity tester, we can see that the lithium is an excellent conductor of electricity. If we add a piece of lithium to water, one of the things that we notice is the fact that the lithium floats. Group 1 metals are less dense than water. We also see that the lithium reacts very rapidly with the water. This is a single displacement reaction producing hydrogen gas and lithium hydroxide. So lithium hydroxide is very water soluble and dissolves in the water. The hydrogen gas escapes. If we trap some of the gas in a test tube, we can test that the gas is actually hydrogen by testing its flammability. We can test that lithium hydroxide
is indeed produced here. And so which one reacted most violently so far? Potassium for sure. Potassium's the biggest, it's going to react the most violently. Let's see if they do cesium. This is lithium in water. Here, it doesn't react so violently. Let's see. Fast forward.
So, this here is a lithium metal, and the lithium metal, you'll notice,
this is a big piece of lithium. If you did that much potassium, there would be a huge flame right now. If you put that much potassium in, there'd be a explosion. Basically, that was a huge feat. That's what it would look like. So what's going on here? Because isn't that, when we look at the redox chart, lithium should be the strongest reducer, and then followed by number 2, which is potassium. But when you look at the observations are just the opposite. Potassium reacts much more violently than lithium. And so what's going on here? What's going on here is this. When we look at this chart's based on where it finally ends up. Where it finally ends up is this. Initially, the reaction with potassium is much more violent. But what happens is it forms a little bit less stable ion. Potassium ions are kind of big, and so they aren't as stable as small ions in water. And so initially you get a large release of energy, and then not much. Lithium, you don't get much release of energy initially, but there's a slow release of energy because lithium ions are so tiny that they interact with water very favorably. And so over the long haul, lithium is going to go lower in energy than potassium would. But it's just slower, it's less violent because we're looking at the production of lithium ions, not the initial oxidation of the metal. And so even though lithium is ranked as number 1, it's not the number 1 in terms of violent reactions. It's number 1 in terms of production of energy. Rubidium would be much more violent. Cesium would be the most violent out of this slide here. The oxidizers want to do the opposite. So you want small for oxidizers, you want big for reducers. Yeah. Here's a slide summarizing the biggest atoms, bottom left, the smallest atoms, top right. Skip this. In the video, they talked about ionization energy. Ionization energy is the energy required to strip an electron off an atom. This is what we call the ionization energy. So potassium would have a very low ionization energy. It's very easy to strip an electron off. Fluorine would have an extremely high ionization energy. Do you know what would have the highest ionization energy on the periodic table? Actually, francium has the lowest ionization energy. Hmm? Not hydrogen. Helium. Helium has the highest. Helium has the most energy required to take an electron off. Francium has the least energy required to take an electron off. You know what? That follows with size. And so the smaller the atom, the harder it is to take an electron off. The bigger the atom, the easier it is. This is the ionization process. You know, sodium has a relatively low ionization energy. It's 500 kilojoules per mole. So a lot of things can oxidize sodium, including air, water. Water can even do it. And so water comes along, it oxidizes sodium, it pulls an electron off. Sodium's left with 10 electrons rather than 11 electrons. 10 electrons, well, that's perfect. That's like neon. So we end up with the sodium ion. And you see filled shell. Okay. Filled first and second shell. If we look at the ionization energies, they follow the trend in size. What species has the highest ionization energy? Helium. It's the smallest. What species has the lowest ionization energy? Well, look, this is lithium, and then sodium has lower, and then potassium has lower, and then what would be next? Cesium, francium. Francium is going to have the lowest. Therefore, it's the most dangerous. As far as this goes. Fluorine here. Do you see these blips? There's some blips. Pretty much follows size except for these blips in here. Blips. And so we'll go on, you know, smaller size and then bigger size, and then smaller size and then bigger size, you know, go. So as we go across, smaller size, and then drop down, bigger size, and then smaller size, and then start over. Based on the periodic table. And so this is the first row of the periodic table, smaller size, and then we hit the second row. Second row is going to be bigger. And then as we go across, it gets smaller until we get to the end. Then we have to drop down to the next one. Do you see the trend here? The periodic trend. There are a couple of blips in there. Beryllium to boron, and then nitrogen to oxygen. That's what we call the first ionization energy. The second ionization energy is the amount of energy to strip the second electron off. The third ionization is the amount of energy for the third electron, fourth electron, fifth electron, etc. And so in terms of first ionization energy, the hardest to strip an electron off would be the smallest, helium. The easiest to strip an electron off would be the biggest, francium or cesium. List each the following elements in order of increasing first ionization. So which one would be the hardest to strip an electron off? Beryllium, nitrogen, or fluorine? Fluorine. Followed by, and then beryllium. Beryllium would be the biggest of this series here. So fluorine is going to have the biggest ionization energy, and beryllium would have the smallest ionization energy. So we have the family, the alkali metals, all of them have very low ionization energies. So as I said in the video, they're all soft, they're all low density metals, they're easy to cut with a knife. We want to lose one electron, all of them do. Except hydrogen. Although hydrogen is interesting because if you compress hydrogen, the very high pressures, it becomes like a metal, conducts electricity. Solid hydrogen at high pressures conducts electricity, like a metal. Here are the chemical families. Here's lithium. This is lithium reacting with water. Here's sodium reacting with water. Here's potassium reacting with water. Even though lithium is the best reducing agent, potassium is the most violent by far of this series. Over the long haul, lithium will release more energy or release less energy than potassium. More energy. That's why. Over here, this is chlorine. Chlorine wants to do what? It wants to take electrons. So this is chlorine reacting with phosphorus. Chlorine's going to strip electrons off phosphorus. This is bromine reacting with phosphorus. Bromine wants to take electrons. This is iodine reacting with zinc. Iodine wants to take electrons and form zinc iodide. So these are all oxidizers. Out of these oxidizers, which one's the most violent? Chlorine, bromine, or iodine? Chlorine. You can see that it's hard to tell, but it's the most violent reaction there. Then we have these families, you know, the alkali metals, the alkaline earths, the transition metals, the halogens, the noble gas. We call these the chalcogens, pnictogens. There are other names. Or you call them the oxygen family, the nitrogen family. It works too. Lanthanides and actinides. Lanthanides and actinides are filling the F subshell. These metals are less reactive, but still kind of dangerous. So for example, calcium can react with water to form hydrogen gas as well. Magnesium can too, but magnesium is less. We have the noble gases with the filled configuration. And we have the halogens. The halogens are all powerful oxidizers. Chlorine. Chlorine's a gas, bromine's a liquid, iodine's a solid. Look at that liquid though, that's a volatile liquid. Bromine. None of these smell very good. We have metals, nonmetals, metalloids. We talked about this earlier, so I'm going to skip that. But there are certain characteristics of metals that we should recognize. Metals are electron rich, so metals tend to lose electrons in undergoing chemical reactions. Nonmetals tend to gain electrons the closer to the right. Metals have low ionization energy. Nonmetals have high ionization energy. If nonmetals can lose electrons too, so this is a little bit tricky. I wouldn't even bother memorizing the second row. I'd rather just memorize the positive and negative range. Metals form compounds with nonmetals. Nonmetals tend to form compounds with both metals and other nonmetals. Metals conduct electricity well. Nonmetals don't conduct electricity very well, except for graphite. Metals tend to have high thermal conductivity. Nonmetals poor. Metals are malleable. Nonmetals typically are brittle. Not all of them. Some of them are rubbery. Metals are ductile, which means they can be drawn into wire. Malleable means you can shape them into different shapes. And nonmetals tend to be non-ductile. You can't really draw them into wire. So we have the different regions here. At the boundary, what happens is this. It starts off very metallic. So let me start off here. Cesium, we're very metallic, or cesium. As we go across, we become increasingly non-metallic. And it becomes less and less metallic until we hit this region. This region is a transition, where we transition from metal to non-metal. And so in this region, we have the metalloids, the transition region there. It's not the transition element. So what is the most metallic element on the periodic table? francium's the most metallic, or cesium. What is the least metallic? Fluorine or helium. And they want to do different things. So helium's totally unreactive. Okay, so that's a little bit about quantum mechanics. And then we're going to do more. What we're going to do is we're going to look into structure in much more detail and bonding. And so that's going to come with chapter 12 here. So we're going to be starting chapter 12 pretty much. And we're going to be doing 11 and 12 together. And so when we get to 12, which is just a continuation of 11, we're looking at ions next. Cations and anions. So nitrogen, what is some charges for nitrogen? Nitrogen is going to have a charge from +5 to -3. -3 is a common charge for nitrogen. They form the nitride ion. So if you look at nitrogen, Lewis symbol, there's 5 electrons. One way that this can complete its octet is by taking 3 electrons. So if it takes 3 electrons, then we form the nitride ion. There are 2 ways nitride is shown here. This is called the Lewis symbol. The Lewis symbol is going to have these square brackets when there's a charge. And this charge on the outside is the total charge. This is just the formula for the ion. It's called the nitride ion. It's not one of those ones that I wrote down, but it's one of the ones you should know because an IDE anion is just a monatomic typically. Same thing, oxygen has 6 valence electrons. How many does it want? It wants 8 valence electrons or an octet, so it gains 2. Fluorine wants 1, so it gains 1. You can see what's happening with the shells here. Completing the second shell there. Neon's already got that complete second shell, so it doesn't want to change. It doesn't want to lose, it doesn't want to gain. You know? Because if it were to lose, it'd have to lose 8. If it were to gain, it'd have to gain 8. That's not very favorable energetically. And so all these have something in common. Nitride, oxide, fluoride, and neon have a total of 10 electrons, filled first and second shell. The same thing with sodium. Sodium ion, magnesium ion, and aluminum ion all have 10 total electrons, just like neon. With sodium, it's much easier to lose 1, magnesium lose 2, aluminum lose 3, and then we get rid of these. We end up with these. It still costs energy to lose those. Are these a fixed charge? These are pretty much a fixed charge ion. Fixed charge, except 3 of them are missing. Which ones are missing? Yeah. Well, we could have carbide, but boron and carbon, those are going to have more variable. Same thing with these. But these are monatomic, and so nitride. To have a carbon in a -4 is not so easy, and a carbon in a +4 because those are very high charges. Those high charges have to be stabilized by interacting with other species. So as far as having plain old ions go, these are the stable ones. They're more stable ones. There are some that are missing. Fixed charge would be zinc, cadmium, and silver. Zinc, cadmium, and silver. The boron would be +3. Beryllium is +2. It's missing here. Boron's +3. Carbon is +4 or -4 or somewhere in between. Write the electron configuration for calcium ion. Okay, go ahead and let's do that. What is electron configuration? First, when we answer a question like that, we should do the electron configuration for calcium first, and then calcium ion. And so why don't you do calcium first and then calcium ion? Your periodic table is not going to have the electron configuration given. Did you get it? What did you get? Okay, 1s2, well, calcium is this, 1s2, 2s2, 2p6, 3s2, huh? Is that right?
They need 3s.
Yeah, they're missing one, 3s2, 3p6, 4s2. Calcium, 2 plus, oh, they got it here. Right. So, mistake here, typo, this was correct, they lost the 4s2. We could also use the core, noble gas core abbreviations as well. It's like isoelectron Virago. Alright, you know, I have to leave a little bit early today. And so what we're going to do is we're going to end early. I'll stop now, and then we'll continue this next time.